All right, good morning again. Sorry I forgot to click record the first time. Hello, everybody. So as a reminder for the homework for this class, it is completely optional. I do not collect homework, but I encourage you to try the problems out that I posted, because after today's class, you'll be ready to do so. And they'll give you a little bit of extra practice, because the plan is going to be to finish off Standard 1 on Monday, and then on Wednesday, we'll probably be having our Standard 1 quiz. More info on that on Monday. But with that, does anybody have any questions or comments before we get started for today? Why is it a bad idea to try and teach a horse analytic geometry? It's because you shouldn't put Descartes before the horse. Okay, so last time we had talked about how to solve a couple of different systems of equations involving if two shirts and 4 hats cost $22 and 6 shirts and 9 hats cost $57, then I think what you all determined was that a single shirt, actually one was 5, one was 3, yeah, shirt cost $5 and a single hat costs $3 was the unique solution that you found to this system of equations. Whereas with this system of equations, the one where 4 shirts, 5 hats cost $50, 12 shirts and 15 hats cost $150, you all found that got a different type of answer for that one. So what was different about this system of equations than that system of equations over there?
It had no unique solution.
It had no unique solution. In fact, it had, dare I say, infinitely many solutions. The reason being, in this case, the second equation is really saying the exact same information as the first equation. You just multiply both sides by 3. And so if all of the information that we're given about S and H is that 4S plus 5H is 50, well, there's technically infinitely many possibilities for S and H, assuming we have a very whimsical store that allows you to sell at fractional prices. Or irrational prices even. Whereas over here, we were able to find a unique solution to our system of equations. So what I thought we would do before we move on to kind of the next problem is we could talk a little bit about what these solutions meant graphically. So if I were to want to graph the equation 2s plus 4h equals 22, or equivalently 2x plus 4y is equal to 22, we set up a little xy plane here. How would we graph that?
Solve for y and then use as slope, I forgot the name, slope intercept.
And we can solve this for y. If 4y is negative 2x plus 22, so that y is going to be, what, negative 1/2 x plus 11 halves?
No, 11.
So I divide both sides by 4, I get 22/4, which is 11 halves. I need to divide both sides by 4 to get the y by itself. Got me scared for a second there. It's good that you're questioning my arithmetic, because I assure you I will make those sorts of mistakes. So if we graph y equals negative 1/2 x plus 11 halves, 11 halves is about 5.5. So if that's our y-intercept, let's say and if we have a slope of negative 1/2, we'll get a line that looks something like that. And if we do the same thing with our other equation, let's write it as 6x plus 9y equals 57. We could similarly solve for y. We would get 9y equals negative 6x plus 57. or y equals negative 69x plus 57 ninths, which is the same as, what, negative 2/3 x plus,
19.
plus what?
19 thirds.
57 over 3 is 19, 19 thirds, and 19 is prime, so I know 3 doesn't go into it. Whereas 19 thirds is about, what, that's 6 1/3? So that would be like, we go up here, and draw a line with a slightly more negative slope. And lo and behold, it happens to be exactly at the point where x is 5 and our y is equal to 3 that our two lines are going to intersect each other. This graph may or may not be drawn perfectly to scale. But the fact of the matter is, the fact that our system of equations ended up coming up with a unique solution graphically. So let's see. So this top one here was our, came from our 6s plus 9h equals 57. And this other one was our 2s plus 4h equals 22. You can replace s and h with x and y respectively to get that s equals 5 and h equals 3 was the unique point x equals 5, y equals 3 in the xy plane where these two lines intersected each other. So the fact that these lines intersect exactly once tells us we're going to have a unique solution. What's different if we're here? If we were to try and do the same thing, let's see. If we replace s and h again with x and y, we can get 4x plus 5y is equal to 50. So that 5y is negative 4x plus 50. Or y equals negative 4/5 x plus 10. We're going to get a line that, let's see, has a y-intercept of 10, a slope of about slightly less than -1. And we'll get a line that looks something like that. What would end up happening if we were to try and draw out our line for 12s plus 15h equals 150? Or equivalently, 12x plus 15y equals 150. Is what?
It's the same line.
It's the same line?
Yeah.
Golly. So if we solve for y, we'll get 15y equals negative 12x plus 150. If I divide both sides by 15, we'll get y equals negative 12/15 x plus 150 over 15, and that's just 10. Negative 12/15, that looks like that simplifies. If I divide top by 3 and bottom by 3, oh hey, would you look at that? I know, drop the papers, you're done. If you tried to graph that line, it would in fact give us the exact same line at the end. It's a line with the same y-intercept and the same slope, which means it's going to be the same line in the end. And if you want to ask the question of, at how many points do these two lines intersect? At all of the points on the two lines, because they have the exact same points. And since a line has infinitely many points on it, well, there's infinitely many points of intersection that are going to give us infinitely many solutions. Any questions, comments, or concerns? Just to be a little bit sassy, what would happen if we tweaked that second set of that second system of equations a little bit to get 4s plus 5h equals 50 and 12s plus 15h equals 200?
There are no solutions because the lines are parallel.
Parallel? Gadzooks. Well, this one would lead to the equation for a line of what? Y equals -4/5 x plus 10. This one would lead us with, let's see, 12x plus 15y equals 200. 15y equals -12x plus 200. Y equals -12 15x plus 200, which is the same as -4/5 x plus blah, blah, blah. 40/3. We divide top and bottom of 215 by 5. And if we try to graph these two, well, y equals -4/5 x plus 10 would look something like this. And y equals -4/5 x plus 40/3. 40/3 is 13 1/3. So looks something like this. And if we ask the question of at how many points do these two lines intersect? They don't. Because we do in fact get parallel lines. Lines that have the same slope in the xy plane, but do not share the same y-intercept, meaning they're always going to be kind of angled the same way, but never the twain shall meet. We have so much in common. So, algebraically, we could, I think, say the same thing, that there's no solutions, by saying that if 4x plus 5h is 50, well, multiplying both sides by 3, this top equation alone automatically implies 12s plus 15h is 150. And how many values of s and h are there that would make 4s, or that would make 12s plus 15h equal to 150 and 200 at the same time? Unless 150 and 200 happen to be the same number, I would say you can't make that happen. So this kind of gives us the three ways in which we can talk about whether two lines intersect in the xy plane. They can either intersect at a point, which they'll always do as long as they don't have the same slope. Or they could be the same line and thus intersect at infinitely many points. Or we could have sadness in which we have parallel lines with the same slope but are still not the same line, which are never going to intersect at all. Any questions, comments, or concerns? All right, that's everything you need to know about lines. Linear algebra is algebra of lines. You know how lines work. Course done. Well, other than the fact that this course is not just about solving systems of linear equations, we're also going to be looking at the case where what if instead of lines we have planes or hyperplanes, which is a fun word, but it's basically saying what if we have instead of 2 equations and 2 variables we have 3 equations and 3 variables, or 4 and 4, or 5 and 5. Or if I decide to really be mean and give you 6 equations and 6 variables. We need to have some sort of, rest of the standard is going to be coming up with some sort of algorithm, some sort of procedure for how do you solve a system of linear equations when it gets more complicated than just this. And the way we're going to be focusing on this, if you recall last time we solved this system of equations in a couple different ways. I think there's at least one group that used substitution, solved one of these for h in terms of s, plug that into the other equation, use that to solve for s and then for h. And there's another group that used elimination, where you multiplied the top equation by, both sides of the top equation by -3, added the 2 equations to each other, got something that just involved h, or just, yeah, I think something that just involved h. And once you know what h is here, it's pretty easy to solve for s. So the method we're going to be looking at going forward is I'm going to focus on elimination specifically. Namely, how would you solve the same system of equations using elimination? Where, if we flip to the second page of the packet, elimination is a method of solving a system of equations where in elimination we're allowed to do three different things. First thing we can do, we can take any equation and multiply both sides of that equation by a non-zero constant. Second thing we're allowed to do is we can swap the order of any two equations. Because if I asked you to solve 2s plus 4h equals 22, 6s plus 9h equals 57, obviously that would have the same solution set as if I asked you to solve 6s plus 9h equals 57 and 2s plus 4h equals 22. The order in which you write the equations doesn't matter. And finally, and this is the spiciest one, we can take any equation and add a multiple of another equation to that equation. And the slick thing is, if you take a system of equations and all that you do to the system of equations are some combination of these three things are not going to affect the overall solution to your system of equations. Solution or solutions, I should say. Meaning, if you take this system of equations and you replace the top equation with the same one thing where both sides are multiplied by 5, for instance, that's going to have the same solution set as our original system of equations. So let's put that into practice. See if we can somehow solve this system of equations just doing some combination of these three steps. So I want to start with 2s plus 4h equals 22. 6s plus 9h equals 57. It's still really hard to say 6s without making it sound like success. Whenever I draw a double arrow like this, what that means is this system of equations over here is equivalent, meaning it's going to have the same solution set as whatever I draw after the arrow. So let's say we wanted to do the elimination method, where we kind of eliminate one variable somehow in one of our equations so that we're just left with an expression in terms of one variable, which we can do by multiplying equations by something, adding a multiple of one equation to another equation, swapping the order of any two of our equations. What do you think would be a good first step in using these processes to give us another system of equations that's a lot easier to solve?
Maybe multiply the top equation by 3.
Multiply top equation by 3?
Yes.
Sounds reasonable to me. So the way I'm going to denote that is, I'm just going to say, if this is E1 for equation 1, and this is equation 2, I'm just going to draw above this arrow 3 times equation 1 to just say I'm multiplying the top equation by 3, which will give us 6s plus 12h equals 66. And the fact that this has this double arrow means that the solution or solutions to this system of equations should be the same as the solution or solutions to the original system of equations. Neato burrito. Question? Okay. Okay, cool. So what else can we do?
You can times the second equation by -1 and then add the two together.
Ooh, okay. How about this? We could do that in 2 steps by saying, second equation we're going to multiply by -1 and then add equation 1 to equation 2. Yeah. Or we can use the fact that we can add any multiple of any equation to any other equation. To say we can just add, let's say, -1 times the second equation to the first equation. And basically that would accomplish the same thing but in 1 step instead of 2 steps. Technically we could have done that right from the get-go and said subtract 3 times the first equation from the second equation. But I like breaking it up into steps. Well, anyway, I'll just write it down. So what I'm going to do now is we're going to take equation 2 and I'm going to replace it with equation 2 minus equation 1. So in other words, I'm taking equation 2 and I'm subtracting equation 1 from it, thus replacing it. So equation 1 is going to stay the same. Equation 2, well, 6s minus 6s is going to be 0s, or just 0. 9h minus 12h is going to be, and 57 minus 66 is going to be -9. And no, you don't have to write the 0s. Just leave it off. Prefer. Where do you think we can go from here? Solve for h. Substitute that back into the other one. I think we could do that at this point if we wanted to. Use the fact that this system of equations right here is equivalent to our original system of equations. I'm going to do something else first though, just for the sake of a little bit of cheekiness. I'm going to take equation 1 and I'm going to replace equation 1 with equation 1 plus 4 times equation 2. We'll see maybe why that makes sense in a second. So 6s plus 4 times 0s is that's still going to be 6s. What do we get if we take 12h and add that to 4 times -3h? 0h is going to be equal to 66 plus 4 times -9. I think that's 66 minus 36, which is 30. And down here we'll still have -3h equals -9. And then just for fun, we're going to do a twofer. I'm going to do 2 things at the same time. I'm going to multiply my top equation by 1/6. So we'll take 1/6 times the top equation, and we'll take -1/3 times our bottom equation. Which, for our top equation, will give us s equals 5. And our bottom equation will give us h equals 3. And so it turns out that our original system of equations is the same as the system of equations, or has the same solution set as a system of equations that is s equals 5 and h equals 3. If we wanted to take this system of equations and solve for s and h, what would we get?
5 and 3.
I would say s equals 5 and h equals 3 is probably the unique solution to this system of equations, s equals 5 and h equals 3. So by only using the methods of elimination, not only could we get to a point where we could pretty easily solve for s and h, which I would say at this point, if I were doing this by any means, I would just solve for A, plug that back, substitute that back in, solve for S. But just using elimination alone, you can actually get directly to the solution of S equals, in this case 5, H has to be equal to 3. Any questions or comments? So that's kind of how we can get that from elimination. Next one I want to look at, and don't write this one down because we're going to come back to this in a few pages after we talk about some other stuff first, is what happens if we wanted to solve x minus 3y minus 5w equals negative 7, 3x minus 12y minus 2z minus 27w equals negative 33, negative 2x plus 10y plus 2z plus 24w equals 29, and negative x plus 6y plus z plus 14w equals 17. We can use elimination, I claim, to solve this system of equations as well. The problem is, how on earth do we use elimination to solve this system of equations right here? I would actually argue that in practice, it's not that bad to solve this system of equations, but we have to have a plan. We can't just start adding multiples of equations to each other willy-nilly. In order to simplify this down to a point where we can actually solve for x, y, z, and w. Dr. Gersel, why is it x, y, z, w and not w, x, y, z? Shut up, that's just how it's done. We need to actually come up with some sort of algorithm, some sort of plan for how do we go about using some combination of these 3 steps in order to solve that system of equations. And the first thing that we're actually going to do in order to get to that point, which we will in a few pages, is we're going to take our original system of equations and put it in matrix form. So how many of you have seen matrices before in previous math classes? How many of you are fond of matrices? If you raise your hand, you're going to love this class because most of what we're going to do over the course of the semester is going to involve matrices in some way or another. But start things off, before we come back to actually solving this particular system of equations, talk a little bit about what matrices are. I'm going to say that an m by n matrix is a rectangular array of numbers with m rows and n columns. So for instance, if I were to draw out a rectangular array that looks something like 1, 0, 2, 1, 4, 1, 5, 7, 8, negative 8, pi, square root of 2. That would qualify as a matrix. It's made up of a rectangle, and at kind of each point, at each vertex in our rectangle, we're going to be placing down a number. And usually going to be written like this. So I would say that this matrix is a what by what matrix. So in other words, what's the m and what's the n that are going to correspond to this matrix?
4 by 3.
Yeah, this one's going to be a 4 by 3 because it has 4 rows and 3 columns.
Oh.
I think it's actually going to be a 3 by 4. Because we have 1, 2, 3 rows in our matrix and 1, 2, 3, 4 columns to deal with. I have made that mistake many, many, many times before, gotten it backwards. Whereas if we compare that to something like, I don't know, 1, 5, -2, 9 billion, 0. What would be the m and the n in this case? This would be a what by what matrix.
5 by 1.
Technically it has 5 rows and a single column, so we could say this is a 5 by 1 matrix. For something like this, we could also just say, since it only has a single column in it, we could also just call this a column vector. I'll explain in the next standard kind of more formally what I mean by a vector. Similarly, if we had a matrix with a single row in it, we could call that matrix a row vector as well. But if we look back at our original system of equations, where if we had something like along the lines of 2s plus 4h equals 22, 6s plus 9h equals 57, what we're going to be doing going forward is we're going to be creating given a system of equations like this, we can create a matrix that encodes the same data as that system of equations. And the way we're going to do that is we're going to let each row in our matrix correspond to the coefficients on x, y, and the constant on the other side in our system of equations. So that our top row, 2s plus 4h equals 22, is going to become 2, 4, 22. And our bottom row, 6s plus 9h equals 57, how do you think we would write out that row in our matrix?
6, 9, 57.
Yeah, just 6, 9, 57. And voila, we've created a matrix that kind of contains the same, that encodes the same information as our original system of equations. I'm going to make a slight tweak to this matrix. I'm going to draw a line here. And what this is called an augmented matrix. Where I've kind of taken the right-hand column and partitioned it off from the left two columns. Mainly because the 22 and the 57 are encoding different types of information. 22, for instance, is encoding something different than the 2 and the 4. You can think of 2 and 4 as being in the x column and the y column, whereas the 22 and the 57 are going to be corresponding to the constant column. And by putting a bar like this, it makes it clear that we're treating this matrix here as encoding a specific set of system of equations. The ones where we have 2 times first variable plus 4 times second variable equals 22, 6 times first variable plus 9 times second equals 57 as a constant. Yes.
Did it?
Oh. Awesome. Any other questions or comments so far about how we would take a system of equations like this and encode it into a matrix? So, Dr. Erskine, why would we want to do this? What's the point? I'll tell you what the point is. The point of encoding a system of equations like this into a matrix is all of the, well, I erased it now, but all of those steps for elimination that we did over here to get this system of equations down into just the form s equals 5, h equals 3. Instead of doing elimination directly on that system of equations like what we did earlier, going forward, what we be doing is we're going to be doing elimination instead on the matrix that corresponds to that system of equations. And so we're going to have sort of a sequence of matrices where we do eliminate the same steps for elimination, except instead of doing things to each equation, we're going to be doing it to rows of the matrix. Until eventually we get our matrix in a form where it's very easy to read off what the solution would be to the original system of equations from that matrix. Stop looking at my calculus notes for this class. So let's do that. So we have sort of three different things we could do to do elimination for a system of linear equations in equation form. We could multiply both sides of an equation by the same constant. We could swap the order of two equations. We could add a multiple. Goodness gracious. We could add a multiple of any equation to any other equation. I want to look at what are the three three equivalent steps, I should say, that we could do with matrices instead of with the equations themselves. So let's look at this first one. If we want to multiply both sides of an equation by some non-zero constant, like for instance, we started here by multiplying both sides of the top equation by 3. What would that equivalent of doing that be if we were working with this matrix? Multiplying the top equation by 3 in our system of equations would be equivalent to doing what with our augmented matrix here?
Multiplying row 1 by 3.
Yeah, it would be the same as multiplying everything in row 1, including the 22 over here, by that 3. So I would say the equivalent thing to multiplying an equation, both sides of an equation by a non-zero constant, would be to multiply any row by a non-zero constant. We didn't do this earlier for this particular system of equations, but something we could have done is to just swap the order of our two equations. How would that correspond to something with our augmented matrix?
Swapping 2 rows.
Yeah, you could just swap any 2 rows instead of our matrix. And finally, adding a multiple of any equation to any other equation, which we sort of did when we said, oh, let's subtract the first equation from the second one, or add -3 times the second equation to the first equation. What would that be doing to the augmented matrix?
Add a multiple of any other row to any other row.
Yeah, add a multiple of any row to any other row. So instead of doing elimination with the equations, we can do it with matrices instead by just doing the 3 equivalent steps. Taking our matrix and doing what's called row operations to the matrix in a way that puts our matrix in a form where the equivalent system of equations is a lot easier to solve. So let's do that. Just as an example, with our 2s plus 4h equals 22, blah, blah, blah. S plus 9h. If we're going to start with that system of equations, that would be the same as starting with the matrix 2, 4, 22, 6, 9, 57. And we really are going to be doing essentially the same steps we did before when we did elimination on the equations. We're just doing the corresponding row operations instead. So what I think I'm going to start off by doing, just for funsies, is I'm going to take our bottom row, row 2, and I want to replace it with row 2 minus 3 times the first row. I don't know. Something tells me, my intuition tells me that that is going to make, that's going to be useful for us. So in other words, I'm doing step 3 here. I'm adding -3 times the first row to the second row. Which 2, 4, 22. First row is going to be the same. What's our second row of our new matrix going to look like?
0, 3, negative.
Let's see. If we take 6 plus -3 times 2 is going to be 6 minus 6 is 0. 9 minus 3 times 4 is going to be 9 minus 12, -3. And 57 minus 3 times 22 is going to be 57 minus 66, which I think is -9. Intriguing to me. I'm going to go ahead and take our top row, multiply it by 1/2. So I'm just going to take 1/2 times the first row. And at the same time, something tells me multiplying our second row by -1/3 might be helpful to us. Let's see, our top row, that's going to give us 1 to 11. Our bottom row, that's going to give us 0, 1, 3. What do you all think might be a good next step?
I would say set row 1 equal to row 1 minus 2 row 2.
Subtract 2 times the second row from the first row? I like the sound of that. That would give us a way to cancel out this 2 and make it a 0. Let's see, 1 minus 2 times 0 is, well, still 1. 2 minus 2 times 1 is 0. 11 minus 2 times 3 is 11 minus 6 is going to be 5. And our bottom row is going to stay the same. What's up with this matrix? Grandma?
It's the solution.
It's the solution. It's an answer. It gives us our values of S and H. I think so. At least if we were to put it back in equation form, this matrix would give us our solution. So what would be the system of equations corresponding to this matrix? If, let's say, this is our S column, this is our H column, and this is our constant column.
S equals 5 and H equals 3.
Yeah, we'd be getting technically 1 times S plus 0 times H equals 5, which is the same as just saying S equals 5. 0 times S plus 1 times H equals 3, which is the same as saying H equals 3. So we can just say 1S plus 0H equals 5, 0S plus 1H equals 3, which at this point is the same as saying S equals 5. H equals 3. Neato Dorito. Basically the same steps. I think I may have done it slightly differently. Like I think I combined 2 steps. Instead of saying multiply top row by 3 and then subtract, I just said take row 2 and subtract 3 times row 1 right from the get-go. But essentially this is the exact same steps we did with the equations in the earlier to do elimination to solve our original system of equations. And the only reason we would want to put them in matrix form like this, other than the fact that matrices are going to let us do a lot more things in future standards, is it's kind of a nice, more compact notation. You don't have to worry about what's the S, what's the H. All that you have to worry about is your rows and columns. You don't have to worry about the individual writing out the individual variables. But in essence, you're still doing the exact same thing. Do you all agree that being able to write our matrix like this was pretty handy? Having just like 1, 0, 5, 0, 1, 3 made it very easy to just read off and say, oh hey, S has to be equal to 5, H has to be equal to 3. This matrix right there actually has a very special name. It's called the reduced row echelon form of the original matrix. Which, we flip the page. Oh, actually I'm not. I take that back. That's not the next page. So this process that we just did, I called it elimination. But if you want to be a fancy mathematician, a mathematician of culture, you could call it Gauss-Jordan elimination, or Gaussian elimination for short. Where Gauss-Jordan elimination / Gaussian elimination for short. So how many of you have heard of Gauss before? How many of you have heard of Jordan? Yeah, that's about what I figured. So Gauss is one of these like big famous, like top 6 most famous mathematicians of all time, I would argue. Probably around number 5 or 6. Did a heck of a lot of things in math and physics. Jordan did a lot of stuff in math too, especially in topology. By the way, he proved that if you take any simple closed curve, it divides two space into an exterior and into an interior. Meaning if I were to draw any sort of weird loop on a circle, we could say, hey, there's an inside and an outside of that circle. Jordan curve theorem, it's pretty sick. But a lot less famous than Gauss. So sometimes Gauss just gets all the credit and we call it Gaussian elimination. But Gauss sort of did this, came up with this procedure in collaboration with Jordan. So if you want to give them both credit, Gauss-Jordan elimination. Or if you want to give neither of them credit, it's elimination. But basically, whatever you want to call it, elimination is just this method that we did. A method to solve a system of equations using matrices via what's called the elementary row operations which are what we wrote over on the left-hand board there. I'm just going to draw a big arrow. So I don't feel like rewriting these all out. But the whole idea is solving a system of equations by Gauss-Jordan elimination is you take your system of equations, you put it in matrix form, you do some combination of these row operations, elementary row operations, whatever you want to call them, and by doing these things specifically, you're not changing the solution set to your system of equations. So the idea is you take your original matrix, you put it in this super slick form right here, and then you can just read off the solution or solutions to your system of equations from this matrix right here. And that process is Gauss-Jordan elimination. And last thing I want to say for today is to just give a name to this matrix right here. This matrix right here is the reduced row echelon form, which is a fancy way of saying it's the nice simplified matrix from which it's easy to read off or relatively easy to read off your solutions. And with that, I think we'll call it a day. So when we come back on Monday, we're going to use Gauss-Jordan elimination to solve that system of equations, that behemoth I wrote over on the board there. And we'll talk about how you can kind of use a procedure involving the matrices to make the process a lot simpler than just randomly adding and subtracting all willy-nilly. So hope you all have a good weekend, and I will see you all for what I hope to be the conclusion to Standard 1 on Monday.
Thank you.
And good one.